In the previous lecture, we talked about model selection. In particular, we learned about Stein's unbiased risk estimator, SURE. And we applied SURE to radial basis function networks and learned how to compute the optimum number of parameters for radial basis function. So if you remember in the formula of SURE, when we had the true error was basically empirical error plus a constant and plus a term, that this term was a function of the complexity of the model. In SURE, this was derivative of our estimation with respect to observation, which we discussed that this is basically a function of the complexity of the model. Okay, so a general approach for model selection or for complexity control is to add a term which is a function of the complexity to the empirical error. No, I mean this term this particular term is hard to compute. In the case of radial basis function, it was easy to compute, but in general, it's not easy to compute the derivative of estimated function with respect to the observation. It's not easy to compute. But we know that, end of the day, this is a term, it's a function of increasing function of the complexity, where complexity goes up, this goes up. So let's add an arbitrary function, which is increasing with respect to the complexity. So if I want to use, some new notation, suppose that J is my empirical error, which is a function of theta, and theta is parameter of the model, and is also a function of input and function of target variable. So instead of minimizing this, minimize this plus a penalty function, and this penalty function is a function of theta, but it's increasing function. So it has a role similar to this, but it could be completely arbitrary. So this is called regularization. So one way to avoid overfitting is regularization, to add an arbitrary function, increasing function to the objective function, and minimize this regularized objective function instead of the objective function. And there are many different types of functions here that you may regularize. You may add as a regularizer. In neural network that we learned, a very popular penalty function is L2 norm. So if you recall, we learned backpropagation. Using backpropagation, we can do gradient descent, basically, and compute the optimum norm. So if U is weight of the network, then in backpropagation and using gradient descent, we compute U derivative of this error with respect to U, right? That was what we did. And backpropagation helped us to compute this derivative of objective function with respect to weight. If you want to avoid overfitting in neural network, one way to avoid overfitting is to add a penalty function to this error and make a regularized error function. So I make like a regularized error function, which is basically error function plus a penalty function. And a very common penalty function is L2 norm. So I add norm 2 of this weight to the penalty. So instead of taking derivative of this error, now I I need to take derivative of this error and subtract it from u. So the derivative of regularized error with respect to u would be derivative of error with respect to u that I can compute using backpropagation plus derivative of this term that I have added as a penalty, which is going to be u. In fact, I usually have a coefficient here as well. So that would be the derivative of regularized error function. Now, if I want to use gradient descent, my update rule would be u equal to old u minus some learning rate. And now, instead of derivative of error function with respect to u, derivative of error function with respect to u plus alpha u. This is called weight decay. Which is a very common way to avoid overfitting in neural network. So basically, I penalize large weights. I don't let weights to be large. When weights of the network want to become large, here, we had a penalty for complexity. When it tries, when the model tries to get more complex, we penalize it. So here we have a penalty on weight. We don't let the weights of neural network get large. So there are many different factors that can contribute in the complexity of neural network. The number of nodes, the number of layers. These are quite clear. If I add the number of nodes, if I add the number of layers, it's more complex. But here, actually, we don't penalize number of nodes or number of layers. It's usually pretty hard, when you have to fix the structure of your network. You cannot play with the structure of the network during the learning. It's hard. So usually, we fix the structure of the network. Another factor that contributes in the complexity of the network is the size of these weights, which I can penalize. Do you know why size of the weights is a factor that can contribute in the complexity of the network? Why a network with larger size, larger weight, when the size of weights are larger, it's more complex, more flexible. Why is that? The structure is fixed. I have fixed number of nodes. I have fixed number of layers. I'm just talking about weights. Smaller weight, less complex model compared to larger weight. Why is that? Yes?
Because larger weights mean your output's more sensitive to your inputs.
Sorry, larger weight?
A small change in your inputs can have a very large effect on your outputs due to larger weights, right? Which means that you get potentially more complexity in the outcome.
Yeah, that's a good intuitive answer, that larger weight, led you to change the output more radically when you change the input, So it's a good intuitive answer. Another good intuitive answer is that quite often we use a sigmoid function as our nonlinear function. And, close to 0, you see that the behavior of this nonlinear function is almost linear. But when the weight is large, it starts to behave nonlinearly. So when, if you have even a huge neural network, but you don't have nonlinear function, like you don't have the sigmoid at the end of each node. If at the end of each node you just have the summation of input, then the whole neural network, no matter how large it is, it's a linear function, because it's good. The first layer would be a linear transformation, the second layer would be another linear transformation, and so on. And the multiplication of all of this linear transformation would be linear at the end. So no matter how many nodes you have, how many layers do you have, it can be linear if you don't have the sigmoid function. So it is nonlinear because you do have the sigmoid function. So if I control the sigmoid function to behave linearly or more linearly, then I'm closer to linear. When these functions start to behave nonlinearly, then the whole system will be nonlinear. Okay? So here is another like sort of intuitive answer to this question. But let's study this more precisely and see mathematically what's happening when we add this penalty function to our objective function. So that's the objective function that I'm supposed to minimize. That's the objective function that I minimize in practice, adding a penalty function to this. Okay, so this is my objective function. I regularize and add this function to this. In this particular case, my theta is weight, and the penalty function is L2 norm. Okay, and I have derivative of this form plus derivative of this one. That's what I'm minimizing. So in general, this function could be anything, could be like y minus y hat, could be any other type of like entropy function, could be any sort of objective function that I can use here. Let me approximate this function using like Taylor series for two terms. So compute the so let me find the quadratic approximation of J. Okay, as a reminder, in Taylor series, we say, for example, I want to approximate f of x. That would be like f of a plus f prime of a 1 factorial x minus a plus f double prime of a 2 factorial x minus a squared, and so on, right? Okay, so I want to approximate this function. So the approximation of J, let me call it I don't know, J tilde, or this is J. Let's call this regularized function J tilde. And then I call this approximation J hat. So J hat, set A to be U star. When U star is the optimum solution of this case, when I minimize J. Okay, so suppose U star is the optimum solution when we minimize J U x y. It means that derivative of J with respect to U at point u star, let me write it this way. It means that derivative of j with respect to u at point u star is equal to what? Is equal to 0. So that's the optimum solution. Now I use this Taylor series around this point. So in the neighborhood of u star, I'm going to expand this objective function, j, and call it j hat. Okay, j hat is what? So that's a function of u and is a function of x and y. So I need j at point u, a star. So that's j at point u star plus I need derivative of j at point u star, which is, what's this second term? 0, right? Because I assume that u star is the optimum solution. Okay? So j star would be 0. Then I need the second derivative of j. Divide by 2 factorial times x minus a. So second derivative of my objective function, call it H, Hessian matrix, right? Because my objective function, if you take, u is a vector. You take derivative, first derivative of your objective function with respect to this vector is a vector, Jacobian. Then you take this derivative of this vector with respect to the vector again. It's going to be a matrix, which is Hessian, right? It's unknown matrix, but it is a matrix, okay? And it is, I have factor 1 over 2, and I have like x minus a squared, means I have u minus u star transpose times u minus u star. So that would be the second derivative, right? And I ignore the third term and fourth term. So I use Taylor expansion up to the second. Is that clear? Is it clear what we have done so far? What I've done so far is just to approximate my j, because j is, in general, is unknown, right? I don't know what the form of this objective function is. In many cases, the objective function really is quadratic, like y minus y hat squared. It is quadratic function. But I want to be more general, Any form of objective function, even if it's not quadratic, I'm just going to approximate it by a quadratic function using Taylor expansion. And this is my approximation of my objective function. Okay. Now, if I want to do regularization using L2 norm, I have to take derivative of this objective function plus derivative of L2 norm, right? So in regularized form, I have my objective function, which now has been approximated by j hat plus L2 norm this needs to be minimized in regularized form. Okay. I need to minimize this. So To minimize this, I can take derivative of this and set it to 0. So derivative of this term, which now has been approximated in this form. What is derivative with respect to u? Derivative of j hat with respect to u. What's the derivative of the first term with respect to u? 0. What's the derivative of this term with respect to u? Okay, it's h. You know, it's a quadratic function. What's the derivative of x minus a squared with respect to x? It's 2x minus a, right? So it's exactly the same. It's quadratic function. So derivative with respect to u is h times u minus u star. And it's actually 2 times h u minus u star, and I have 1 over half here, and this h and this 2 and 1 over 2 get canceled. Plus derivative of this term with respect to u, which is u. Actually, I have alpha here as well. You know, always I have this alpha. So there's always a coefficient times the penalty function. So it's alpha u. So that's the derivative of my approximation of the objective function plus penalty, which I need to minimize, so I can set this equal to 0. So this is hu minus hu star plus alpha u equal to 0. And I can write it as h. I can write it as h plus identity times au equal to h u star. Right? Now, the solution of this optimization, u, will be h. I have to multiply both sides by the inverse of this function. So that would be h plus I alpha inverse times h u star. Okay. So that would be, if u star is the solution of optimization when I minimize my objective function, u is the solution of regularized objective function when I add a penalty, L2 nor penalty to it. So one observation here is that if alpha is going to 0, then you have h inverse times h, which is identity, then u is going to be u star. So if alpha is 0, so it's clear, if you don't penalize it, the solution is the solution that you had before. But what's going to happen if we do penalize it? When I really add something, what does h plus I alpha inverse mean? When alpha is small or 0, this h inverse cancel this h and the solution will not change. But when alpha is large, how do we change the solution? Okay. Okay, to understand what's happening here, I'm going to go a couple of steps further. I'm going to decompose H using singular value decomposition. You know, you can decompose any matrix using singular value decomposition, right? So I can decompose H using singular value decomposition as phi lambda phi transpose. And any matrix could be like U sigma V transpose when this is diagonal. And these two are orthonormal. Why I said phi transpose? Why I assume that U and V are the same? Because H is symmetric, right? All Hessian matrices are symmetric. Because derivative of f with respect to xi and then derivative with respect to xj, if you switch these two derivatives, the result will not change, right? So all Hessian matrices are symmetric. So that would be the composition of H. Let's substitute this decomposition there. I have phi lambda phi transpose plus I alpha inverse U H, sorry, and H is phi lambda phi transpose times U star. That's my U. Okay. You know, phi is orthonormal because we did singular value decomposition. So it means that phi transpose phi is identity. As long as phi is not truncated, phi transpose is also identity. If you truncate phi, I mean, if you map H to lower dimensional space, if you get rid of some of this direction, then phi transpose is not identity. But if you don't do that, if you keep all of eigenvalues is in lambda, don't set any of them to 0, keep all directions, then phi transpose is I. Okay. Think about decomposition of H. You remember, you know, when we decomposed, when we applied singular value decomposition to X, when X was actually normalized, it was PCA, right? And PCA gives us directions of variations of data, X. And then eigenvalues was the magnitude of this direction, you know, the variance of this direction of variation. Now, when you decompose Hessian matrix here, as if basically you are considering all orthogonal directions of H, direction of variations of H, and corresponding variance of each direction. Okay, so I mean, the concept of this decomposition will be important in our analysis later on. Just think about it, that what this decomposition conceptually means. Okay, so I know phi transpose phi is identity as long as it's not truncated. Phi transpose is also identity. So I will write this as phi lambda phi transpose plus, say here, actually, I just put identity matrix. Phi transpose. You know, phi transpose would be identity, and then I can you know, this is identity, right? I can, instead of this identity, put phi transpose. I can write it this way. Since it's identity, since alpha is just a scalar, I can also write it this way. Makes no difference, you know. Okay, now if I simplify this one more a step, you know, I can just keep this lambda plus I alpha inverse inside. Now look that this phi transpose phi, this phi transpose phi is identity because I have orthonormal matrix. And actually, you know, this, because of this inverse, this is going to be phi transpose, and this is, no, this is right. Okay, phi transpose phi would be identity here. Then I have phi lambda plus I alpha inverse lambda phi transpose U star. Okay. So U, the new U would be phi, which is an orthonormal matrix, lambda plus I alpha inverse, lambda phi transpose U star. Okay. Now suppose that alpha goes to 0. If alpha goes to 0, I have lambda inverse here times lambda is identity. Then it's going to be phi transpose U star, and phi transpose is identity, so it's going to be U star. But phi is orthonormal matrix. It's like a rotation matrix, right? So we can think that what's happening when alpha is 0 is that I rotate my solution U star using this phi, and I rotate it back. It's orthonormal matrix. You know, phi and phi transpose are inverse of each other. So I rotate it, and I rotate it back. So nothing will change if alpha is 0. But if alpha is not 0, what's going to happen? Look at this term. And don't forget that lambda is diagonal matrix. So lambda has this form, like lambda 1, lambda 2, up to lambda d. And here everything is 0. Okay, so then this lambda plus I alpha have this form. Lambda 1 plus alpha, lambda 2 plus alpha, and so on. Lambda d plus alpha. And then you take inverse of this. Which is 1 over lambda 1 plus alpha, 1 over lambda 2 plus alpha, 1 over lambda d plus alpha. Okay. Now, lambda plus I alpha times lambda, I multiply this by like lambda 1, lambda 2, lambda d. It's going to be like lambda 1 divided by lambda 1 plus alpha. This is lambda 2 plus alpha, and so on. Okay. This is this matrix. So in ith dimension, what is the value of lambda I divided by lambda I plus alpha? It depends on the value of alpha, right? Suppose that alpha is small. Then what would be this value? 1, right? So if alpha is small, so if it's smaller than alpha I, then this is almost 1. But if alpha is greater than alpha I, then what would be this quantity? It's almost z. Okay, what does it mean? It means that what's happening here is that first I rotate my solution, U star, by phi, I rotate it. Then I multiply each direction by this quantity. This quantity depends on the value of alpha I, lambda I, could be close to 1 or close to 0. If I have a lambda I, which is quite larger than alpha, don't forget what was alpha. Alpha was the coefficient of my penalty, right? If alpha is quite larger than alpha, then it's almost 1. This is eigenvalue of one direction of this Hessian matrix. In this direction of Hessian matrix, eigenvalue is large. Means it's a significant direction for minimization, This Hessian actually told me that we are minimizing the objective function. We are looking at the second derivative, and we decompose this second derivative in different directions, orthogonal to each other. And this lambda shows the importance of each direction, the variance of each direction. If this direction is a significant direction, if it's a direction which is going to help minimization significantly, it's very steep, then it's almost 1. So it means that on that direction, U will not be changed. Because in that direction, I rotated everything. In that direction, this is almost 1. So, and then I rotated back. So nothing will change in that direction. But if it turns out that lambda I is way smaller than alpha, means that direction is not a significant direction for optimization, then it's almost 0. And I rotate it using phi, then it's going to be very small value, close to 0. So I shrunk that direction, and then I rotate it back. So it means that talking about significant directions for optimization, we don't, that U will be almost intact. We don't change U after adding the penalty function. But if it's not an important direction, then we shrunk that direction. We shrunk that value. We set it almost to 0. When you have U, if you set U to 0, haven't you changed the complexity of the model? You did, if I have this weight is 0, as if it doesn't exist, as if there is no connection here. So it does change the complexity of the model. So basically, the effective complexity would be different because of the size of this U. Okay? So that's what L2 norm does. L2 norm basically keeps some of the direction if they are important, shrunk some other directions if they are not important in terms of optimization. And through this basically shrinkage, reduce the complexity of the model. You know, this factor actually is called efficient parameter, or effective parameter. So if you want to know the effective complexity, what the effective complexity is, you can compute this summation over all I. If all of them are significant, you know, and you have D direction, it's going to be D. But if some of them are not important, then some of them would be significantly less than 1, close to 0, and they have no effect. So you have D directions, but this summation would be significantly less than D. And it depends on the value of A. The larger the value of A is, the larger, the more directions will be shrunk to 0. Okay? Is any question? So do you know what's going to happen if instead of L2 norm, if I add L1 norm to my objective function? So L1 norm, you know, here actually we shrink this direction, make it small. If it's L1, you set it to 0. You just not make it small, you just make it 0, exactly 0. So the solution would be sparse if you add L1 norm instead of L2 norm. Not about neural network. In general, in regularization, I'm sure you have heard this term, lasso. Lasso is a technique that basically you add L1 norm to your objective function to make the solution sparse. You know, suppose that you're doing a simple least square, and you're solving y minus b transpose x. If you add L2 norm of beta, then some of the directions of beta becomes small. But if you have L1 norm of beta, then the solution would be sparse. I mean, some of this beta will be 0, which is pretty good actually, because you know you can use it in variable selection, for example. You know, you have this x, it's your measurement, and you have measurements about everything. But you don't know which of these variables are important in predicting this y. You know, you want to predict real estate, for example, and you have the price of, like, you know, real estate price, you have prices of homes and lands and so on. But you don't know really what are the important factors for real estate. You know, it's you know, information rate. It's income of people. It's the number of people sitting in this city, number of people who are, you know, coming to this city from other cities, from other countries. How much are their income in the country that they are coming from? Maybe they just want to buy, you know, this house cash. And there are many, many factors that you can conjecture that they could be possibly influential. And you collect all of this data. Now you want to fit this model, simple regression model. This is it's the long vector, okay? If beta is not sparse, you are assuming that all of them are important in your prediction. They may not be. You don't know. You just, had some conjecture, some guess, and you collected those data. So, but if you make this beta sparse, means many of these are going to be 0. So they cancel out that direction. Basically, your optimization will tell you that this is not an important factor if you want to predict this, The fact that how much money they make in their, original country has nothing to do with, say, for example, the fact that they are going to buy a house here or they are not. Example. So it's going to get rid of some of this direction. So you can do variable selection if it's sparse. Okay. Sparsity is pretty important, and it has been practiced in the area of neural network as well. So some people, instead of weight decay, they add L1 norm. But if you do L1 norm, then the solution is not as clean as this one, because L2 you can take derivative, right? But if it's L1, you can't take derivative. The function is not differentiable as this form. You can't take derivative of that. And then solution is not as clean as this one. Recently, by recently I mean since 2009, there is a very good solution for lasso and sparsity that people didn't know or didn't use before 2009. Before 2009, there were solutions mainly based on linear programming and so on. But since 2009, there are solutions based on coordinate descent. So coordinate descent means that you have a high-dimensional vector that you want to optimize, but you optimize each direction separately. And coordinate descent, in general, is a very bad way of optimization. If you look at good books in optimization, like if you look at Stephen Boyd's book on convex optimization, you can't find even coordinate descent in that book. It hasn't been even mentioned. It's not a good technique. But it turned out that in this particular case, it is really effective and good. And so if you go for each direction separately, I'm talking about L1 norm of a vector. If I consider only one element of this vector, so it's going to be a scalar, and L1 norm would be absolute value, right? So it's easy. Absolute value, I can consider two cases. It's either positive or negative. So I can write it as two functions. Now I can take derivative of that. For each direction, so I can solve it analytically, in closed form. So coordinate descent is basically based on this. So you're going to have closed form solution for each direction separately and set some values to 0, which is, it's very useful not only here, everywhere, if you can find almost in any cases, if you can find a sparse solution, in 99% of the cases, is a better solution than a dense solution. If you can find a low rank solution, in 99% of the cases, it's a better solution than a high rank solution. Intuitively, that's basically what's going to happen. That's like L1 norm in 2 dimension. And when you have this objective function with L1 norm, when you have this objective function with L2 norm, it's like that this is your objective and this is your constraint, because you can show that it's like a constraint. So when you are minimizing, it's as if you're growing this or you are making this closer to this until they touch each other, but they don't cross each other. So, and they touch at some point, this circle will touch this circle at some point, and that will be your solution to the optimization. But when you have L1 norm and your objective function wants to touch this, it can touch it mainly or most of the time in one of these corners. So the chance that this touches this here or here is way more than touches anywhere else. And this means that the solution will be a sparse. So in 2 dimension, if we touch it here, this direction is 0. Or if we touch it here, this direction is going to be 0. That was the main intuition in the first paper of Lasu. But you can justify this more like theoretically. You know, you can say that, in fact, I explicitly want beta to be sparse. So basically, I have to add, as a penalty, I have to add the cardinality of beta. So I want the cardinality of beta to be a small, means L0 of beta should be a small, but L0 is a non-convex constraint, and convex envelope of L0 would be L1. So let's add L1. That would be the best approximation of cardinality, which makes the solution sparse. Okay, so I don't do the analysis for L1 norm here, but it's similar to this one. Make everything 0, and it's better solution if you can handle it, but it's not as clean as L2. It's not as easy as L2. Any question? Okay, in the new literature of neural network, basically in deep learning, there are many other ways for regularization, which we don't go through them in this class. But one way is adding noise to the input. One way is adding noise to the weights. You can show mathematically all of them are sort of regularization. It's similar to adding a penalty function. So you have a very clean data, add a little bit noise to your data. So it helps to avoid overfitting, and you can show mathematically why it happens. Or you can add a little bit of noise to the weights that you're learning. It helps to avoid overfitting. And a more new technique is dropout, which is a very successful method, but very easy to implement, which is basically setting half of the weights of each layer to 0 in each iteration. So randomly choose half of the weights, set it to 0, learn. And in next iteration, just set half of the weights to 0, and then do the iteration again. So we can show that it is one way of like doing ensemble methods, like as if you're, one way in classification is one like hypermodel in classification or in any type of modeling is bagging, that we are going to learn later in this course. And bagging means basically taking vote between many different models, as if instead of one classifier, you train many classifiers and then take a vote of them, and you can show that it performs better than one classifier. Mathematically, you can show that it always, under some condition, performs better than one classifier, one individual classifier. And dropout is some sort of bagging, because randomly you're setting some of the weights to 0 in each iteration, as if your model in the next iteration is different from the model in this iteration, A structure has been changed, Some weights in this case is 0, some weights in the other case is 0. So some of the nodes are not active here, some of the nodes are not active here. It's two different models. As if you're fitting different models to the data, and then you're taking the average of them. It's one implicit way of doing bagging, which performs pretty well. Okay, any question? Okay. So our next topic would be support vector machine. In short, it's called SVM. By the way, before I talk about support vector machine, one project for final project, one suggestion actually that we're working on, an idea for final project is, you see how we apply SURE, Stein's unbiased risk estimator, to RBF to avoid overfitting. As a problem that you can work on, it could be a good project for final project. Can we apply SURE to backpropagation and neural network? It's not as easy as RBF. In RBF, we were able to compute this derivative in closed form. We cannot compute this derivative in closed form for general neural network anymore. But the approach that we took to compute this derivative using backpropagation, can we take the same approach and compute this derivative? Using chain rule and backpropagation. So if you can compute this, then you have a good regularizer for neural network. If you're interested in this project, we can talk about it in my office or after the class. There are some extensions of SURE that we haven't discussed in class. In 2009, there is some extension on SURE to apply, which can be applied to exponential family in general. So that can be, you might be able to apply this to general neural network. Any question before we start support vector machine? Okay, so support vector machine is a classifier. Could be linear, could be nonlinear, but we start with linear case. So we start with linear case, and then we see how it can be extended to nonlinear case. So it's support vector machine. Basically, when you have two classes, in perceptron, we learned that perceptron is going to find a linear decision boundary between these two classes, somewhere, right? Support vector machine is going to find decision boundary between these two classes, but it's going to find one of those infinite number of possible solutions, because perceptron can find any decision boundary in here. But support vector machine is going to find one of those infinite number of solutions, the one which has maximum margin to both classes. Means the one that is right at the middle. So it has maximum distance to this one and has maximum distance to this. So the main intuition was that it's a better solution compared to other solutions. And in fact, mathematically, you can show that it is a better solution compared to any other solution that doesn't satisfy this. Okay? So for the moment, our assumption is that data is separable. So there exists a linear decision boundary, which can divide the data perfectly. And when data is linearly separable, there are infinite number of solutions. And among this infinite number of solutions, we are looking for the one which is right at the mid, has maximum margin. Okay? So the goal is to maximize the margin of decision boundary. Okay. So how can we do this? How can we find a solution which has maximum margin? So when we did perceptron, we looked at the geometry of this decision boundary. I'm going to quickly, remind you, the properties that we showed for a decision boundary. If this is a boundary beta transpose x plus beta null, any point on this boundary satisfy equation beta transpose x plus beta null equal to 0, right? So So beta transpose x1 plus beta null is equal to beta transpose x2 plus beta null equal to 0 for any x1 and x2 on the decision boundary. So it means that beta transpose x1 is equal to beta transpose x2, and it means that beta transpose times x1 minus x2 is 0. So we concluded that beta is orthogonal to x1 minus x2. So we concluded, if you remember in perceptron, that beta is orthogonal to this boundary, right? So that's direction of beta. So that was one property. The other property was that beta transpose x null plus beta null is equal to 0 for any x null on decision boundary. So beta transpose x null is equal to minus beta null. That was the second one. Now, if I have a point here that I would like to find the distance of that point, like point x, to this decision boundary. Do you remember what we did? We projected to like orthogonal direction, right? So you can choose an arbitrary point here, x null, compute this distance between x and x null, and project this distance on the direction of beta. Then it's going to be the distance of your point to the decision boundary. So for any point x, you can compute x minus x null, then project it on the direction of beta, and that would be your distance if beta is normalized, right? So you have to make sure that beta is normalized. So to make sure, actually, we divide it by the norm of beta. Make sure that beta is normalized. That will be our mid distance. So this is beta transpose x minus beta transpose x null divided by norm of beta, which is beta transpose x minus beta transpose x null is just beta null divided by norm of beta. Okay. So again, this D could be positive or could be negative, depends on the side of the decision boundary. So we have the general setting that we had so far, you know, that it's binary classification and data have this form. xi, yi, I equal 1 to n. and yi could be -1, could be +1, depends on, I mean, there are two types of classes. So this D depends on the side of this decision boundary. It could be negative, could be positive. You want to make it positive. So how did we do this in the case of perceptron? Just multiply this by I, right? So if I multiply this D for a particular I by yi, that would be the positive distance of point X to this decision boundary. So this is in fact, in support vector machine, this is in fact my margin. Right? So when I said that I want to maximize margin, and I had two set of points, it means that, there's one point which is quite close to this margin. I want to maximize that margin. Or let me just say that this is my distance, because margin would be the smallest distance among all possible points, right? So I have, this is my decision boundary, and there are many points here. Each of them I can compute the distance. The margin would be the distance between the closest point, right? Okay. So margin would be minimum of di yi over all I. The smallest one would be the margin. So in support vector machine, we would like to maximize the margin. Okay? So it means that I need to maximize the shortest distance between a point and the decision boundary. So margin would be di times yi, and when this is my di, so I have beta transpose xi plus beta null times yi divided by norm of beta. This is my margin. Yes? Yes. We have to maximize the margin. I'm not doing the optimization now. I'm just defining the meaning of margin. Yeah, SVM maximize the margin, finds the decision boundary which has this, the maximum distance from both classes. But what is the meaning of margin? If you look at this decision boundary, there are many points here, and you can compute the distance of all of them to this decision boundary. Margin is the distance of closest point to this. So margin is the distance of, if you look at the distance of all of the points to this, margin would be the shortest one. Then you have to maximize that. basically, eventually have to maximize this minimum. Okay? So any question here? So if I want to minimize this, this quantity should be a small, and this quantity should be large, right? Okay. So I'm not going to start going through the details of this optimization. We're going to do this next in the next lecture. But just to, give you a direction that what we are going to do, let me just show you something here. You know, this yi times beta transpose xi plus beta null. Okay. This is the distance when it's normalized. This is the distance from the decision boundary, right? For all points that are not on the decision boundary. For the points that are on the decision boundary, this is 0. For the points that are not on the decision boundary, this is greater than 0, strictly, right? So suppose that there is a small value, C. None of them are 0. So there's a small value C that I can say everyone is greater than equals C. Because none of them are on the decision boundary, right? Are you happy so far? You know, do you agree with me that I can write for all points that are not on the decision boundary, I can write this. So if I divide both sides by C, then this is going to be 1, right? So beta transpose divided by C, beta null divided by C is just, you know, some coefficient of this vector and some constant number. So let's call it beta star and beta null star. It's greater than equal 1. So there I can change beta in a way that the distance of points from the boundary is always greater than equal 1. Okay? I can do it always. You know, I can rescale this beta in a way that the distance of points that are not on the decision boundary is always greater than equal 1. So the minimum distance is 1. So for some beta, the minimum value here would be 1. For some beta. And then I have to maximize that beta if I want to minimize this quantity. Okay? If I want to minimize this quantity, I have to minimize this fraction. I have to minimize this quantity and maximize denominator. So you remember, you know, in many cases we put, you know, a cap on denominator or denominator and then optimize the other one. This is the same concept. You know, suppose that the maximum value of this is 1 and then optimize for beta. But it's not a wrong assumption because you always can, you know, rescale beta in a way that the minimum value of beta is 1, distance is 1. So this value is at least 1. No point is closer than 1. So you can set this 1 and then just go for maximizing this. Then in next lecture, we can see that you can start from maximizing this subject to some constraint. You know, that would be one of the constraints. And then we can write a convex optimization formula to find the optimal solution. Any question? Question?
So this is all under the assumption that this is linearly separable, right?
Yes, yes.
So because otherwise this marginality would be a big issue, right?
Sure. You know, now for the moment we assume that we have only two classes. We assume that the decision boundary is linear. We assume that data is linearly separable. Then we relax these assumptions later on. You know, we see that if decision boundary is not a linear decision boundary, what can we do? So with one extension, you can take care of nonlinear cases. Then we will see that if data is not linearly separable, what can we do? You know, this is called hard margin when data is linearly separable. And we have soft margin for the case that data is not linearly separable. Any question? Okay, see you on Thursday.